Welcome! In this explainer, we're going to unpack the technology that's powering just about everything these days, from your phone's camera to the future of medicine. I'm talking about artificial neural networks. We're going to look at not just how these digital brains work, but why they are such a massive shift in how we think about building intelligent machines.
Okay, so let's just dive right in with a really big question. Most software we use is built on a very rigid set of rules, right? Instructions written by a programmer. But what if? What if a program could go beyond that? What if it could adapt, improve, and actually draw its own conclusions from the world around it? This right here, this is the fundamental idea that makes neural networks so different from everything that came before.
And this slide really nails that difference. Think about traditional code. On the left, like a chef who can only follow a recipe word for word. If you're missing an ingredient, the whole thing just fails. A neural network, on the other hand, is more like a master chef who's tasted thousands of different dishes. It doesn't just follow the rules, it starts to understand the principles behind good food. It can improvise, adapt, and even invent whole new recipes.
So, where did this revolutionary idea even come from? Well, the ultimate blueprint, the original source of inspiration, it's actually sitting right inside your head.
Yeah, the pioneers of this field. They looked at the human brain and saw a completely different way to compute things. Instead of one big central processor doing all the work, they saw this massive, tangled web of neurons, all interconnected. They had this realization that billions of very simple units, these nodes, all working together, could create incredibly complex intelligence. So an artificial neural network is basically our attempt to build a digital version of that amazing structure.
Okay, so let's get into the nitty-gritty of how this whole thing actually works. We're going to build our digital brain from the ground up, starting with just one single, really simple component.
And here it is. This is the fundamental building block of the entire network, the artificial neuron, or sometimes it's called a node. By itself, it doesn't do a whole lot. But just like in our own brains, when you connect millions or even billions of them together, that's when something absolutely incredible starts to happen.
Now, what's really interesting here is step 2, the weight. A weight is basically just a knob that dials up or down the importance of a connection. So when a neuron gets a bunch of signals, it doesn't treat them all the same. A high weight means, hey, this signal is super important, pay attention. A low weight means, this one's not so important. And it's by adjusting millions of these tiny little knobs that the entire network actually learns how to do something useful.
Now, these neurons aren't just a chaotic jumble. They're organized into a very neat, structured system of layers. You have data coming in through the input layer. Then it gets passed through one or more of these hidden layers. That's where all the really complex thinking and pattern recognition happens. And finally, a result, an answer, comes out of the output layer.
You've heard the term deep learning thrown around everywhere, right? Well, this is all it really means. A deep network is just one that has multiple hidden layers, at least 2. And the reason that's so powerful is that it lets the network learn patterns at different levels of complexity. The first layer might learn really simple stuff, like edges or colors. The next layer might combine those to recognize shapes, and a deeper layer could learn to recognize complex things, like a face or a car.
So we have the structure down, but how does it actually learn anything? I mean, this is where the real magic comes in. A neural network isn't born smart. It has to be trained. And the way it learns is, funny enough, by making a whole lot of mistakes.
To get a feel for this, just imagine we want to teach a network to tell the difference between a starfish and a sea urchin. We'd start by feeding it a huge data set of thousands of pictures that we've already labeled. For every single picture, the network has to make a guess.
And here's the key. Every time it guesses wrong, this super clever process called backpropagation kicks in. It figures out exactly how wrong the guess was, and then it works its way backward through the entire network, making tiny adjustments to all of those weights we talked about earlier. It's basically asking, okay, which connections led me to this mistake? And then it dials them up or down just a little bit. That's it. That's how it learns.
So at the very beginning, all those weights are just set to random numbers. So its performance is, well, it's terrible. It's pretty much just guessing randomly. But after just a few hundred guesses and hundreds of those tiny little corrections from backpropagation, it's not random anymore. It's actually starting to pick up on the visual patterns, the textures and shapes that separate a starfish from a sea urchin.
Now you repeat that process thousands and thousands of times. Show it an image, it makes a guess, you correct the error, it adjusts its weights, and eventually the network becomes incredibly accurate. It has effectively taught itself how to see the difference, all by continuously minimizing its own mistakes.
So here's a really important point. While a lot of these core ideas have actually been around for decades, it took a kind of perfect storm for them to go from theory to, well, to changing the entire world.
You can see some of those big moments on this timeline. The basic idea of a neuron, the perceptron, that was way back in the 50s, and backpropagation got popular in the 80s, but the real explosion, the moment things went vertical, was in the 2010s. You had game-changing moments like AlexNet in 2012, which proved deep learning was king for image recognition, and then the Transformer in 2017, which is the architecture that now powers pretty much every large language model you've ever heard of. So why now? What was so special about the last decade? Well, we're in this golden age of AI because we finally have the perfect recipe. First, the algorithms themselves, like the ones we just saw, are way more sophisticated. Second, thanks to the internet, we have these massive data sets to train these models on. They are very, very hungry for data. And third, we finally have the computer hardware, especially GPUs, with enough raw power to actually run these gigantic calculations. And the result of all that coming together is that this technology is now absolutely everywhere. It's helping doctors diagnose diseases, it's powering the speech recognition on your phone, it's filtering your spam email, it's even creating new art and music. Neural networks are quietly reshaping pretty much every part of our world.
But, and you knew there was a but coming, with all this incredible power comes some really important challenges, some big problems and responsibilities that we absolutely need to talk about.
One of the oldest and biggest criticisms is what's called the black box problem. Because the network learns on its own, its decision-making process, that massively complex web of millions of fine-tuned weights, can be almost impossible for a human to really understand. We can see that it works, but sometimes we have no idea why it works.
And this black box issue leads us to a huge real-world problem: dataset bias. See, a neural network knows absolutely nothing about the world except for the data we feed it. So if that data has existing human biases in it, racial bias, gender bias, you name it, the network won't just learn those biases. It will often amplify them.
The Amazon recruiting tool is a famous, or maybe infamous, case study of this. They trained a system on a decade's worth of their own hiring data. But that historical data was dominated by male applicants. The result? The AI taught itself that male candidates were just better, and it started systematically penalizing any resume that even had the word women's in it. It's a really stark reminder that these systems are only as unbiased as the data we give them.
And all of this leaves us with a final, really big question to think about. We are building digital brains that are learning from the world that we have created, from our language, our pictures, our history, and our behaviors. So as this technology keeps evolving and shaping our future, maybe the most important question isn't just about what these things can learn, but about what we believe they should learn.